Okay, so today we're going to be talking about Chapter 3 on radiation characteristics. This goes along with Chapter 3 in your text starting on page 24. So now that we've talked about the different kinds of images that you'll be taking as a DA, this chapter covers characteristics that affect the quality or outcome of your images. You're going to be hearing new terms like milliamperage and kilovoltage that you may or may not have heard of, but it's kind of important for you to know what these terms are to help you understand the science part of radiography. Some of the questions that are going to be answered in this chapter are the following. What are the differences between X-ray beam quality and quantity? What is the difference between kilovoltage and milliamperage? And what is the inverse square law and what relevance does it have to dental radiography? These are some of the questions that will be covered on the RHS exam for the state of Arizona, so it's important to know them. Some of the things that are covered in the Chapter 3 reading are the following. X-ray beam quality, X-ray beam quantity, and X-ray beam intensity. So the purpose of this reading is to detail the concepts of X-ray beam quality and quantity. We're going to define the concept of beam intensity, and we're going to discuss how exposure factors influence these radiation characteristics. So X-ray beam quality has to do with voltage and kilovoltage peak, and how density, contrast, and exposure time have to do with kilovoltage peak. So the wavelength determines the energy and the penetrating power of radiation. In dentistry and in medicine in general, we really want the shorter wavelengths that have more penetrating power. These are the types of x-rays that are going to penetrate the skin and surrounding tissues to get through the tooth, the pulp, the bone, and then out the other side to the receptor. And the only x-rays that are going to be able to do this are going to be the short, zippy wavelengths with lots of power. The quality is used to describe the mean energy or penetrating ability of the X-ray beam. The quality is controlled by kilovoltage. Try to associate the word quality with kilovoltage. So now we're going to be moving on to voltage and kilovoltage. So voltage is a potential between two electrical charges. Voltage is a potential difference between two electrical charges. When voltage is increased, the speed of electrons is increased. So voltage is the measurement of electrical force that causes electrons to move from the negative cathode to the positive cathode inside the machine. The electrons that strike the target, and this happens inside the machine where the x-rays are being produced, with more force and energy if a higher voltage setting is used on our x-ray machines. So voltage is measured in volts or kilovolts. And in dentistry, we use kilovolts because we need enough power to get through all the tissues in the mouth. A volt is a unit of measurement used to describe the potential that drives electrical current through a circuit. A kilovolt equals 1,000 volts. Dental radiography requires the use of 65 to 1,000 kilovolts. Less than 65 kilovolts will give you an inadequate penetration to where your image is going to be too light. Likewise, something greater than 1,000 kilovolts is going to give you overpenetration and will result in a picture that's too dark to read. So talking about kilovoltage peak or KVP, the kilovoltage peak is the maximum or peak voltage. This usually refers to the peak voltage of an alternating current. A polychromatic X-ray beam is produced as a result of a varying kilovoltage in the tube current. So an X-ray travels in waves, not necessarily a constant beam. So if a dental X-ray tube is set to 70 kVps, there is an alternating current, but the maximum kVs delivered are going to be 70. If the machine is set to 80 kVs, although there is an alternating current, the maximum kVs delivered is 80. So the maximum or peak voltage simply refers to the setting on the X-ray machine. The quality or wavelength and energy of the X-ray beam is controlled by the kilovolt peak. Density in kilovoltage peak. So density is something you will hear over and over again. Density is the overall darkness or blackness of an image. If the kilovoltage is increased, the image will appear darker and have more density. If the kilovoltage is decreased, the image will appear lighter and exhibit less density. Contrast in kilovoltage peak deals with contrast and how it relates to kilovoltage peak. So we could think about contrast when we think about a black tux and a white shirt. There's going to be a lot of difference or contrast between a white shirt and a black jacket. In radiography, we also blend in some different shades of grays. The whiter parts of the image are known to be radiopaque, while the darker parts of the image are known to be radiolucent. In low kV settings, we get an image with a higher contrast. This gives us images that are mostly black and white with more crisp borders, which are more pleasing to the eye. These images are useful for detecting cavities. High kV settings create a low contrast setting with lots of different shades of gray. These may not be as pleasing to the eye because of the different shades of gray can make things harder to distinguish. These are good for detecting bone level for periodontal disease or periapical issues, which are the tip of the root of the tooth. This is sort of counterintuitive because you would think that a higher kV setting would give you more contrast and a lower kV setting would give you less contrast, but this is not true. Contrast and kilovoltage are inversely related. So a low kilovoltage setting will give you a higher contrast, and a high kilovoltage setting will give you a lower contrast. Okay, so exposure time and kilovoltage peak and how they relate. Exposure time measures the amount of time that the X-rays are going to be produced. It's also measured in impulses because X-rays are created in a series of bursts or pulses rather than in a continuous stream. It is determined by a setting on the control panel such that whatever time you select, that's how long X-rays are going to be produced while you press the trigger button on the X-rays. It's important to note that an adjustment in exposure time is necessary when kilovoltage peak is increased. Failure to do this will give you an image that is too dark or too light. X-ray beam quantity refers to the amount of X-ray beams being produced inside the machine and pass through the tissues and onto the receptor. So we're going to be talking about amperage and milliamperage, milliampere seconds, density and milliamperage and how they relate, and exposure time and milliamperage and how they relate. So again, X-ray beam quantity refers to the number of X-rays produced in the dental X-ray unit. Amperage and milliamperage. If you remember from chapter 2, there is an anode and a cathode inside the X-ray machine, and the average talks about how much current is flowing between the two. So the amperage determines the amount of electrons passing through the cathode filament. Increasing the amperage results in an increased number of electrons traveling from cathode to anode and the production of increased number of X-rays. The more X-rays that are available to penetrate an object, the more dense or dark the X-ray will be. So the quantity of the X-rays produced is controlled by a milliamperage setting. Typically in dentistry, we use between 7 MAs and 15 MAs. So both amperage and milliamperage are measurements used to describe the number of electrons or current flowing through the cathode filament. A milliampere is 1/1000th of an ampere. In dentistry, we use the milliampere. In dental radiography, milliamperages range from 7 to 15 MAs. Exceeding this produces excessive heat, which will produce an excessively dark image. Milliamperage regulates the temperature of the cathode filament. A higher milliampere setting increases the temperature of the cathode filament. It then increases the number of electrons produced. And if the number of electrons produced increases, the number of X-rays emitted from the tube are also increased. Increase in number of X-rays permitted also increases the intensity of the X-ray beam. So the quantity of the number of X-rays produced is controlled by milliamperage, because as the cathode filament is heated up, more electrons are produced and more X-rays are produced. Milliampere seconds is a product of milliamperes and exposure time. When milliamperage is increased, exposure time must be decreased to maintain constant density. This is a better way to express a combination setting for the milliamperes and button time or exposure time used. So what would an X-ray with increased milliamperage exhibit? Well, it would be too much density. The X-ray would be too dark. A way to counteract this would be to reduce the exposure time. Density and milliamperage are related in the following way. If we increase our milliamperage setting, our overall density of our radiograph increases, causing the image to be too dark. Now, exposure time and milliamperage have an inverse relationship. When milliamperage is increased, exposure time must be decreased because we don't want a lot of current flowing through the machine with a long exposure time. That's going to make a really dark, harder to read image. When milliamperage is decreased, exposure time must be increased because with the weaker flow of current, we are going to want to expose the receptor for longer to allow enough density for our image. So the X-ray beam intensity refers to the strength or power of the beam, and it's related to kilovoltage peak, milliamperage, exposure time, distance from the source of the radiation all the way to the receptor, which would be the sensor or the X-ray film, something called the inverse square law, which we'll cover in just a minute, and a half value layer, which is a safety device inside the X-ray tube. So the X-ray beam intensity is a product of the quantity or number of X-ray photons and quality or energy of each photon per unit of area per unit of time of exposure. Kilovoltage peak regulates the penetrating power of the X-ray beam by controlling the speed of electrons traveling between the cathode and the anode. Higher kilovoltage peak settings produces an X-ray beam with more energy and shorter wavelengths. So kilovoltage peak controls the amount of contrast and also the amount of kinetic energy produced. So if you think of a flashlight that you find in your garage and the battery is dead, it's going to produce a beam of light with a low intensity, sorry. Similarly, if you were to put a higher or a new battery inside the flashlight, the intensity of light is going to be stronger. This is the same thing as if you were to increase the kilovoltage peak settings in your X-ray. You're going to get a more intense X-ray beam, just like you would get a more intense beam of light by replacing the battery on your flashlight. Once again, with milliamperage, this controls the penetrating power of the X-ray beam by controlling the number of electrons produced in the X-ray tube and the number of X-rays produced. Higher milliamperage settings will produce an X-ray beam with more energy, increasing the intensity of the X-ray beam. Exposure time affects the number of X-rays produced. A longer exposure time will allow for more X-rays, and thus giving you a more intense X-ray beam. Distance refers to the distance traveled by the X-ray beam and how it affects the intensity of the beam. There's three distances that you'll need to consider here. Target to surface, which is the source of the radiation inside the X-ray beam, inside the X-ray cone to the patient's skin. Target to object, which is the source to the patient's tooth. And then there's target to receptor, which is the source to the receptor or the X-ray film or X-ray sensor. So as the X-rays travel from the point of origin, they diverge and spread out to cover a larger surface area. The intensity of the beam then lessens. So if you think back again to the flashlight, and if you were to turn your flashlight on, and this time you do have a full battery, and you're going to put the flashlight so you're almost touching the wall. okay, you're going to notice that the beam of light is going to be more intense, and it's only going to cover a certain or a small or narrow area. Now, as you pull that flashlight back from the wall, you'll notice that the light covers more of the wall. It'll cover more of the wall, but as you go even further and further away, you'll notice that the beam of light becomes less and less intense. The same thing happens to your X-ray beam. The inverse square law states that the intensity of radiation is inversely proportional to the square of the distance from the source of radiation. So when the distance is doubled, the beam is 1/4 as intense, so it's going to lose its intensity by a factor of 4. When the distance is halved, the beam is 4 times as intense, so it will gain intensity by a factor of 4. Again, with the flashlight example, and the inverse square law works with light as well. In fact, from what I understand, photographers use this law for stage lighting as well, where if you double the distance your flashlight is from the wall, the light intensity is going to decrease by a factor of 4 or will be 1/4 as intense. Likewise, halving the distance from your flashlight to the wall will increase the intensity of light by a factor of 4, or the light will be 4 times as intense. The half layer value has to do with the safety device inside the machine. The half value layer has to do with the safety device inside the machine. So we said earlier that X-rays aren't constant, but instead pass through as pulses, and these pulses are all different in lengths. We also said that we want short X-rays in dentistry because those are the ones that are going to be powerful enough to penetrate the tissues in the mouth. So these filters, which are like aluminum plates that are placed inside the X-ray tube, remove the unwanted or unnecessary long wavelengths and allow the more useful, more powerful short wavelengths to pass through. So overall, this increases the mean penetrating capability of the X-ray beam while reducing the intensity. The thickness of a specified material that reduces the intensity by half is termed the half value layer. So, does the half value layer reduce the intensity of the X-ray beam? Well, yes, the X-ray beam intensity is reduced by half. So this gives us an idea of the characteristics of radiation for chapter 3. Thanks for listening, and I'll see you tomorrow.